All right, well, this is Mrs. Schneider. I'm recording the Honors Review Guide, spring of 2015, for the final exam. For both your benefit and mine, I'm going to go as fast as I can. If you need more information on any specific question, you can find them in your old review guides or you can email me. All right, let's jump right in. So, electrostatics, it asks us to be able to use Coulomb's law and the law of ones to solve problems. So Coulomb's law looks like this. It's the first equation on the equation sheet under electricity. K Q1 Q2 over D squared. So it's telling us the distance between the two charges is doubled, the magnitude of one charge is tripled. To use the law of ones, we put in ones for anything that's not changing. K will never change, it's a constant. One of our Q's is staying the same. One of our Q's is becoming a 3. The distance is doubling, so it's becoming a 2. And it's squared, which is super important, because our final answer will be 3 over 4. So the magnitude of the force would be 3/4 as large as it was originally. That's not a very good 3, sorry guys. All right, now what is force directly proportional to? If you look at the equation, as charge goes up, force goes up. So it is directly proportional to the charge. However, how is it related to distance? Since distance is in the denominator, as distance goes up, charge actually goes down. So force is inversely related to distance. Now, an electroscope was the funny looking thing in a jar that we kind of talked about. I could never get the one in my classroom to work very well, but it consisted of two metal leaves inside. If you touched it with a charged object, the leaves would split apart. If you touched it with a neutral object, the leaves would continue to hang straight down. So an electroscope is a device used to test for electric charge. All right, now name the four fundamental forces and list them in the order of strongest to weakest. This should be pretty easy because we just finished learning about the strongest, which is the strong nuclear force. The trickiest one is probably the weak nuclear force, just because we haven't really learned about it, but it goes next. Then you have electromagnetism, then gravity. Gravity, surprisingly, is the weakest of the fundamental forces. All right, now we're going to look at the three ways to charge an object. Don't get these confused with the three ways to pass heat. They are sort of similar. Conduction is charging, I'm so bad at spelling, charging through direct contact. Electrons physically move. And your two objects will have the same charge. I don't have room to write that, so I'll just say it. Your two objects in this case will end up with the same charge. Induction is charging by being near. So bringing a charged object near a neutral object, no electrons move. It's not permanent. Friction is charging by rubbing objects together. So electrons do physically move, and you end up with opposite charges. Again, if you want more detailed explanations of those, you should go back and check your old reviews. That's probably the best way to study for this. All right, give the charge for each of the following. Electrons have a negative charge, protons have a positive charge, and neutrons have a not applicable because they are neutral. All right, if an object gains electrons, it becomes, so gaining electrons means it will be negatively charged. And if an object loses electrons, it will be positively charged. That's a little bit counterintuitive, so make sure when you're asked a question like that that you just stop and think through it for a moment. All right, using arrows and words, explain how a test charge would move in an electric field. Well, we draw electric fields as how they would affect a positive test charge. So say we wanted to draw an electric field, we would think about, okay, the fact that if we had a positive test charge, this field would push it to the right. So that's how we would draw the whole field. We'd be like, woo. Say instead the field would push the positive charge down into the paper. Then we would draw symbols like this. Awesome. Okay, draw a strong positive charge and the electric field surrounding it. Do the same for a strong negative charge. Alright, I'm going to kind of do these off to the side. So here's our positive charge. Here's our negative charge. Remember, for both of these, we draw how they would affect that little positive test charge. So this would repel the positive test charge. It would be like, no, get away. We'll draw lots of arrows because that shows the strength of the field. The negative one would pull the positive test charge in. It would be like, all right, come here, you. Again, lots of arrows because it's said for it to be a strong charge. Let's make it clear what those pictures are for. Like charges repel, opposite charges attract. Grounding is giving excess charge. God, spelling. What? Excess charge to the earth or the ground. We can then pretend that the ground is neutral because the ground has so many electrons and protons already that even if we give it a whole bunch of electrons, like the amount contained in a strike of lightning, you're still going to be neutral-ish. We pretend that the ground has infinite particles. All right, current electricity. So list the factors that affect the resistance of a wire and state how they are related to resistance. There are three factors: length of the wire, okay, I was right. I shouldn't have second guessed myself. So the three factors that we're going to worry about are length, width, and temperature. As length goes up, resistance is going to go down. That is wrong. That's the wrong way to think about it. Resistance is how hard it is for charge to flow through it, and that's wrong. As length increases, resistance increases. As thickness increases, resistance decreases. Imagine a water pipe. The wider the pipe is, the easier current will flow, so resistance goes down. As temperature increases, resistance decreases. The warmer it is, the easier it is for a charge to flow. Alright, now we're supposed to draw the schematic diagrams for all of. Okay, so I need to take a step backwards for a second. This is actually a thing that I taught you wrong in the unit, and then I had to go back and correct myself. And I was just about to try to teach you wrong again. For a resistor, so as a piece of, for a conductor, like a piece of wire, as the temperature goes up, typically the resistance also goes up. Again, that's something that we learned wrong during the unit. I then had to go back and correct myself, and then I got confused again. Alright, now we're going to move down here to these circuit diagrams. A fuse or circuit breaker will look like this. It'll be a squiggle. That's showing that it can be opened. A battery will be a series of lines like that. A load, this can refer to anything that's using the electricity of the circuit. For us, that is most traditionally a resistor, but it can also be a light bulb. A switch is drawn like this. It's usually drawn open to demonstrate that it can be open. Alright, next we have this chart for units and symbols. Current, we use an uppercase I for current, and it's measured in amps. Resistance, we use an uppercase R, and it's measured in ohms, which is given by the Greek letter omega. Voltage is easy. Its symbol is an uppercase V. Its unit is volts, which is also an uppercase V. Charge, we use the symbol Q, sometimes also little q. The county is really weird about when it uses big Q and when it uses little q, and that has a charge, a unit of coulombs, which is represented by C. Now, distinguish between a primary cell and a secondary cell, or a storage cell and a primary cell. Storage, for our purposes, we called secondary. Secondary cells are rechargeable. Primary are not. Pretty simple. They both, just FYI, both of these turn chemical energy into electrical. Alright, according to Ohm's law, how are current and resistance related to each other? So this is Ohm's law, V equals IR. So current and resistance, the way to think about this is if we hold voltage constant, as current goes up, what has to happen to resistance? And the answer is that it would have to go down to keep voltage the same. So they are inversely related. Current and voltage, on the other hand, if we're holding R constant, for current to go up, voltage would also have to go up, so those are directly related. Conductors have loose or free valence electrons that they're willing to pass around, which is why they are good at conducting electricity. while the valence electrons of blank are tightly bound. Well, the opposite of a conductor is an insulator. All right, a portable compact disc player, oh man, a Walkman, receives its energy from a 9-volt cell. The current used to operate the player is 135 amps. How much power in watts does the CD player use? How much energy in kilowatt hours does it use for a 3-minute song? Okay, well, here's what we're given. We're given a voltage of 9 volts and a current of 135 amps. We're going to go to our handy formula sheet. Under electricity, we happen to have a formula for power that is, whoops, you can't see it, that is P equals IV. So I'm going to say P equals IV, 135, and the answer to that is 1,215 watts. Wait, did I write that down right? Yes, 1,215 watts. How much energy in kilowatt hours does it use to play a section 3 minutes long? Well, it should occur to you immediately that we never ever use minutes. Now, typically we would convert from minutes to seconds, which would be multiplying by 60, but we're specifically told that we want to deal with kilowatt hours. So we're actually going to change our time of 3 minutes into hours, which is going to involve dividing by 60. So 3 divided by 60 is 0.05 hours. Then we're going to go back to our formula sheet and find P equals E over T. Rearranging that means energy equals power times time. Now we want it in kilowatt hours, so we've gotten our time in hours, but our power from the last problem is still in watts. To go to kilowatts, we move the decimal 3 places, so it'll be 1.215 kilowatts. 1.215 times 0.05, this is going to be a relatively small number. 215 equals 0.061. I'm going to round to there. Kilowatt hours. Those are funny units, but if you were asked for the cost, those are the units you would need. Alright. Parallel and series circuits. When it says the 3 cardinal rules, what it means are the way current, voltage, and electricity behaves for each one. You don't have to memorize these, guys. They are on the formula sheet. You just have to remember that those are important. I'm going to state them in words on here, although they're stated in formula form on the formula sheet. So, for series circuits, voltage adds up to battery. Current is always the same. Or, as I'm going to write it here, current is the same everywhere. And 3. Sorry for moving my paper around so much. 3. Resistance adds up. Parallel circuits are a little bit different. Rules 1 and 2 are basically switched. Voltage is the same. Current adds up. And it's the third one that's a little bit funny. Resistance in a parallel circuit, the inverses add up. What I mean there is that the formula looks like this. So you have to take the reciprocal of each resistor and add those up. Alright, that's going to help us answer number 2. How are voltmeters connected in a circuit? How are ammeters connected in a circuit? The key to this, again, is not memorization. It's realizing that if you're using a voltmeter or an ammeter, you don't want it to change the measurement that you're trying to get. Now, we want voltage to stay the same for the voltmeter and current to stay the same for the ammeter. So we choose parallel or series based on which of those stays the same. So voltage stays the same in parallel. So voltmeters are attached in parallel. Current stays the same in series. So ammeters are attached in series. What type of current circuit has only one path for current? That is series. In this type of circuit, what happens to one light if the others burn out? They're going to all go out because there's no other path for the electricity to take. What type of circuit has multiple paths for current? That would be parallel. In this type of circuit, what happens to the other lights if one light burns out? The others will stay lit because the current can just take different paths. Practice using the rules to add resistors in series, parallel, and combination. Series and parallel are going to be pretty simple. Combination gets weird. What is the sum of two 30 ohm resistors in series? So this is literally 30 plus 30. So our answer is 60 ohms. The next one's a little bit more difficult. What is the sum of two 30 ohm resistors in parallel? So that's going to be 1 over our total equals 1 over 30 plus 1 over 30. So 1 over our total equals 2 over 30, since they have a common denominator. Then we're just going to take the reciprocal of both sides. So our total is 30 over 2, or 15. So 15 ohms. But here's the more difficult one. What is the sum of two 30 ohm resistors in parallel added to a 30 ohm resistor in series? Now you want to add the two that have the same type first. So there are two that are in parallel, so we're going to combine them first. We just discovered that 2 in parallel would be 15. So basically we just combine these two. So now we have one 15 ohm resistor and one 30 ohm resistor, and these are in series with each other. So at this point we can just add. So our total ends up being 45 ohms. Just be really careful when you work through these. Combine things that are like first, and then combine things that are different. These two were both in parallel, so we combined, oh god, you can't even see where I'm pointing. These two were in parallel, so we combined them first. Then this was parallel and this was series, so we combined them second. Yes, I have a box with a Kraken on it. I'm struggling to find the next page of this thing. Okay. Use the circuit diagram to the right to answer the following. Alright, well here's our circuit diagram. We have 3 resistors. They're all in series. They've given us 2 voltages. This is V total, since it's the voltage of the battery. This is V1, since it's the voltage across resistor 1. So if we wanted to set it up like a chart, which is a thing that I did, V, I, R, and we're going to have V1, V2, V3, V total. So, V total, not the greatest chart. V total is 12. Oh no, it's 18. I can't even read numbers, you guys. V total is 18. V1 is 6. Alright, we know those two things. R1 is 2, and R3 is 3. Now, you look for places where you have 2 pieces of information because that means you can find the third. Remember that you're always going to be using some variation of Ohm's law, V equals IR. So if you rearrange that for I, it's going to be V over R. So we have V and we have R for the first resistor. So we'll do 6 divided by 2 is 3. Now we're dealing with a series circuit, so the current is the same everywhere. If the current is 3 here, it's 3 through the second resistor, it's 3 through the third resistor, and it's 3 total. So now things become pretty trivial because we have 2 pieces of information here. To find V, we would do 3 times 3, which is 9. Now we have 3 pieces of information this way. We know that the total is 18. 9 plus 6 plus something has to equal 18. Let me scoot over a little. Do that up here. 18 equals 6 plus 9 plus x. 6 plus 9 is 15. So we have 18 equals 15 plus x. That means that x has to be 3. Now we have 3 plus 6 plus 9 is in fact 18. Now we have 2 pieces of information here. R is going to be V over I. So 3 over 3 is 1. Now we have all of our, now there's actually 2 ways to find our total. That's good. That means we can check our work. One way is just to add up the resistances. So 2 plus 1 plus 3 gives us a total resistance of 6. Now the other way to check that would be to do V over I. 18 divided by 3 is in fact 6, so yay, both of our methods work out the same, which means we've probably done the problem right. So then we just have to transfer things over to what they actually wanted. I1 was 3 amps, I2 was 3 amps, I3 was 3 amps, V3 ended up being 9 volts, V2 ended up being 3 volts, and R2 ended up being 1 ohm. Alright, describe alternating and DC current. DC current, okay, DC current is actually repetitive because DC stands for direct current. So DC travels in one direction. Come down here to write some more. AC switches directions. And in America, it switches 60 times per second, which is pretty fast. Which type of current is from a battery? That would be DC. And which type is from an outlet? That would be AC. All right, now we're moving from electricity to magnetism. North poles are going to, just like charges, when you're dealing with poles, opposites attract, likes repel. So a north pole would repel another north pole, and a north pole would attract a south pole. What protects our Earth from cosmic rays? What natural phenomenon does this cause? So it's our magnetic field that does the protecting. And the phenomenon it causes is the aurora borealis, which I cannot spell, so I'll put the common name, which is northern lights. On a test, it would almost certainly use the term aurora borealis, so I apologize for my inability to spell that. Okay, I actually would have done a better job than I thought if I had just guessed, because it's actually pretty much the way it sounds, aurora borealis. Alright, what element makes the best magnet? That would be iron. What elements are in an Elenco magnet? These are the secondary elements that make pretty good magnets, and it comes from their atomic symbols. We have Al, which is aluminum. Ni is nickel. And Co, which is cobalt. So iron makes the best magnet, but aluminum, nickel, and cobalt are also magnetic. How could you make an electromagnet out of a nail, a wire, and a battery? You would wrap the nail in wire, run current, which would be from the battery, through the wire. Remember that an electromagnet's strength is depended. Oh, okay. What could you do to make the electromagnet stronger? You could have more iron in the core. You could have more loops of wire. And you could more current through the wire. Now, what are some things you could do to damage the magnetism of a magnet? You cannot cut it in half. That does not work. You could drop it repeatedly. This would have to be seriously a lot of times. And you could heat it up. You have to be heating it very hot. What does breaking a bar magnet into two pieces do? It does not decrease the magnet. It gives you two magnets. Alright, so now we have some energy conservation questions. An electric motor converts what into what? Well, electric. It converts electric energy into mechanical energy. A generator is the opposite of a motor, so a generator converts mechanical to electrical. Yay! Michael Faraday and Joseph Henry discovered that electric current can be produced by the motion of a magnet. More specifically, the voltage is induced in a loop of wire if there is a change in the magnetic field in the loop. This phenomenon is called magnetic induction. When a magnet is plunged in and out of a coil of wire, voltage is induced in the coil. If the rate of the in and out motion is doubled, the induced voltage would double. If the number of the loops was doubled, the voltage would double. It depends, the voltage induced depends directly on both of those, the number of loops and the how fast the magnet is moving. Alright, that's where I'm going to stop for the first half of this video. We'll pick